Hi, class. We're going to finish chapter 2 today, modeling with linear functions, by moving into section 2.4. And what section 2.4 is talks about slope as what's called a rate of change. Okay, so the ratio of a to b is a fraction a to b. So whenever someone says, oh, like 5 to 4 or 3 to 4, it's just a fraction, like 3 to 4 would be 3/4. And so a unit ratio is a ratio written as a to b with b is equal to 1. Okay, so it's what's saying is how much is a changing when 1 changes by 1, basically. All right, suppose a quantity y changes steadily from y1 to y2. All right, well then as a quantity x changes steadily from x1 to x2, then the rate of change, the slope, okay, of y with respect to x is the ratio of change in y to the change in x. So we're used to seeing slope as change in y and change in x, or y2 minus y1 divided by x2 minus x1. So here's an example. So the enrollment at, let's say, DeVry University declined approximately steadily from 82,000 students in 2012 to 37,000 students in 2016. So let's find the approximate rate of change of this enrollment. Okay, so the change in enrollment. So you're going to take the Y2 value, okay, minus the Y1 value. So the change in enrollment here, okay. So it's going to be 37,000 minus 82,000. And you're going to divide that by the change in years. So it went from 2016 to 2012. Excuse me. So you get minus 45,000 students divided by, excuse me, wow, excuse me, 4 years here. All right, so simplifying this into that unit analysis, what we're saying here is it lost, all right, 11.25 thousand students each year. So we're just changing the denominator to a 1 here. Basically, we're taking the 45 and dividing it by the 4. So the rate of change of enrollment was about minus 11.25 thousand students per year. So we can say that enrollment declined yearly by about 11.25 thousand students. All right, the median of a group of numbers is the middle number. So here's another example, okay, where the numbers are listed from smallest to highest. In Phoenix, Arizona, the median house value of a two-bedroom home is 151,000, and the median value of a four-bedroom home is 274,000. So find the approximate rate of change of the median value of a home with respect to the number of bedrooms. Okay, so I want to find the rate of change of the median value of the home. So that tells us the price is going to be in the numerator. With respect to the number of bedrooms is going to be in the denominator. So to be consistent in finding the signs of the changes, assume the number of bedrooms increases 2 to 4 and that the median value increases from 151,000 to 274,000. All right, so the change in the value of the median home, well, a 274,000 home with 4 bedroom minus the 151,000 homes minus 2 bedrooms. You can see that's the subtraction, and then dividing this out, it's $61.5 thousand. So the rate of change of the median value with respect to the number of bedrooms, all right, it looks like that rate of change is about 61.5 thousand per bedroom. Okay, so the median value of a home, like each additional bedroom you stack onto the house, goes up $61.5 thousand. All right, so another way. Suppose a quantity T affects or explains a quantity P. If P increases steadily as T increases steadily, then the rate of change of P with respect to T is positive. Similarly, if P decreases steadily as X increases steadily, then the rate of change of P with respect to T is negative. So here, suppose a student drives at a constant rate. Let's let D be the distance in miles right here. The student can drive in T hours. So some T values are shown here. So after 1 hour, the student has driven 60 miles. After 2 hours, they drive 120 miles, so on. Okay, after 5 hours, they've driven 300 miles. Create a scatter plot, then draw a linear model. Okay, find the slope of the linear model, find the rate of change of distance traveled from each given period, compare each result with the slope of the linear model, and then do it from t is equal 2 to 3, and then from t is equal 0 to 4. All right, so if you draw a scatter plot, then draw a line through the data, you'll see that it's a perfectly linear line like this, actually. And then just picking 2 points, all right, you can see that the change in y is 60 with the change in x here. You can see that the slope is 60. So the slope formula here is m is equal to the change in y over change in x. So with t and d variables, we have d2 minus d1 over t2 minus t1. So arbitrarily, you can use the points 2, 120 and 3, 180, like we did back here, 2, 120, 3, 180. And you can find that that slope, d2 is 180 minus d1, 120, divided by t2, which is 3, minus t1, which is 2, is 60 over 1, or 60. So the slope of this line is 60, like I said previously. All right, let's calculate the rate of change of distance traveled from t is equal to t equals 3. Well, at time 3 hours, the student has driven 180 miles. At 2 hours, they've driven 120 miles. So that rate of change is also 60 miles per hour here. So the rate of change looks like it's equal to the slope. To see the same thing, actually, if you do it for 4, I'm not going to talk through it, but you'll get the same exact thing. That the rate of change here is constant no matter what, and it's always equal to 60 miles per hour. So if there is a linear relationship between the quantities t and p, and if t affects or explains p, then the slope of the linear model is equal to the rate of change of p with respect to t. So if there's a linear relationship, the slope is that rate of change of the variables. All right. So again, suppose a quantity t affects p. All right, if the linear relationship between t and p, then there's a rate of change of p with respect to t is constant. If the rate of change of p with respect to t is constant, then there's a linear relationship between t and p. Let's do an example about finding a model. So a company's profit was $10 million in 2010 and has increased by $3 million per year. Let P be the annual profit in millions of dollars at T years since 2010. Okay, so this is important. We're starting T at 2010, and we know that what the profit was. The profit in 2010 was $10 million. So just remember that when T is equal to 0, because that's 2010, the profit was $10 million, right? And then it's gone up, and it's telling you that it's gone up $3 million per year. All right, so here are the questions. Is there a linear relationship between T and P? Find the p-intercept of the linear model, find the slope, and find an equation. All right, because of the rate of change of the annual profit is constant at $3 million per year, the variables in T and P are linear related. So constant rate of change means there's a linear relationship. The profit was $10 million in 2010, like I was saying. Because 2010 is 0 years since 2010, we can represent this relationship as an ordered pair, or 0, 10. So the p-intercept of the linear model is that 0, 10. So the rate of change of the annual profit is $3 million per year. So remember, slope is the rate of change. So the slope of this linear model is 3. So an equation of the linear model here can be written in the form p is equal to slope times t plus b. Because the slope is 3 and the p-intercept is 0, 10. We have the p-intercept, or we have p is equal to slope 3 times t plus 10. So the ordered pair 0, 10 shown in the first row of the table in your graphing calculator, if you were to plug this in, means the profit has $10 million in 2010, which checks, that's what we want. Also, as the input increases by 1, as you go 1 year to 2 years to 3 years, whatever, the output increases by 3. So this means the annual profit increases by $3 million per year, which also checks. All right, we perform a unit analysis of the model's equation by determining the units of the expression on both sides of the equation. The simplified units of the expression on both sides of the equation should be the same. So I'm going to walk you through this unit analysis. So a driver fills her car 12 gallons, her car's 12-gallon gasoline tank and drives at a constant speed. The car consumes 0.04 miles per gallon. So let's let G be the number of gallons remaining in the tank after she has driven D miles since she filled up. Okay, so kind of the same first 4 questions. Is there a linear model between these variables D and G? Find the G-intercept, find the slope, find the equation, and then let's do this unit analysis. Okay, since the rate of change of the gallons remaining with respect to distance traveled is constant, so it's going down 0.04 miles per gallon, constant rate of change. Okay, the variables D and G are linearly related. When the tank was filled, it contained 12 gallons of gasoline. So with we can represent this by an ordered pair as the person has driven, she has driven 0 miles, so comma, it has 12 miles of gasoline. Okay, so that's the G-intercept, the amount of gasoline remaining. So the rate of change of gasoline remaining in the tank with respect to distance traveled is minus 0.04 gallons per miles. So the slope is negative 0.04. And thus an equation of the linear model can be written in the form G is equal to md plus b. So the slope is minus 0.04 and the G-intercept is 0, 12. We obviously have that the gallons remaining in the gasoline is equal to minus 0.04 times the miles driven plus that starting value 12. Okay, so the unit analysis. Gallons. The slope, the rate of change, gallons per miles, gallons. So what I'm going to do here is I'm going to take this gallons per mile, okay, and make sure that it's the same thing on both sides here. So gallon divided by miles times miles, right here, plus gallons is equal to gallons plus gallons. So basically what I'm doing here is multiplying everything by miles. That's just equal to gallons. So we can see here that the gallons cancel out. So the unit on both sides of the equations are gallons. So this suggests here, okay, that the equation is correct because those miles cancel out. All right, let's do another example. So the percentage of Fortune 1000 board seats filled by women are shown for various years. Okay, so let's let P be the percentage of seats filled by women at T years since 2000. So a model of this situation is given by this equation. P is equal to 1.03T plus 13.55. All right, you can see that as time has gone on, the percentage of women on these boards has gone up. That's great. So using a graphing calculator, here's what I want to do. I want to draw a scatter plot and the model in the same viewing window, check whether the lines come close to the data points, what is the slope of the model, what does it mean in this situation, and find the rate of change of the percentage of seats filled by women from one year to the next. Let's compare the rate of change with the results found in problem 2. And 2020 Women on Boards has set a goal that women will fill 20% of Fortune 1000 board seats by the year 2020. Let's see if that model predicts that that goal will be reached. Okay, so draw a scatter plot and model in the same viewing window. You can see if you do that in your graphing calculator, plotting the data and drawing the line through it like we've done in previous videos, the model, that equation does a really good job predicting or modeling the relationship. All right, the slope here is 1.03 from our equation, because that's in that form y is equal to mx plus b. So according to the model, the percentage of seats filled by women are increased by about 1.03 percentage points per year. Okay, that's the rate of change. The rate of change of the percentage of seats filled by women are shown, okay, here. All the rates of change are close to 1.03. So if you just do the rate of change from year to year, okay, really just you're looking at the difference that it's gone up each year. You see that it's gone up pretty close to 1.03, so our model is a pretty good job there. If we substitute 10 into the equation because we want to predict by 2020, remember T here is years since 2010. If you plug that in, you'll get 23.85. So according to the model, about 23.9% of Fortune 1000 board seats will be filled by women in 2020, so the goal will be surpassed. That's great. All right, just a common warning here. It's a common error to be vague in describing the meaning of the slope of a model. For example, a description such as the slope means it is increasing. Neither specifies the quantity that is increasing nor the rate of increase. So the following statement includes the missing information. So the slope of 1.03 means the percentage of Fortune 1000 board seats filled by women increased by 1.03 percentage points